Awesome. Thank you, everybody, for coming this morning after the conference dinner. And we have Kiati Mayan today talking about the stellar streams in the Milky Way and their simulation. So please take it up.
Yep. Thanks, Sophia. Hello, everyone. Good morning. It's a pleasure to be here. And I'd like to thank the organizers for arranging this workshop, also giving me this opportunity, and also appreciate your decision to schedule Stellar Stream workshop after the Dwarf Galaxy Conference, thereby respecting the causality of galactic evolution. So yes, I'll be talking about streams of the Milky Way in particular and their simulations, the way we run and the kind of problems we run into, and then how do we take care of those. And I would like to excite you about this by showing you this visualization of the Milky Way and some of the streams that we have detected that you can see here. So these are not n-body simulations. Each point that you see is actual Gaia star, and we just map that in the galactic coordinates. So yes, you can also see probably some of the names of some of the streams. Maybe you've worked with a few of them or maybe not. So yes. And in the beginning, I would like to congratulate all of you. One of the metrics to measure health of an academic field is, of course, the number of papers it produces. That's one of the metric. So it seems to be growing for the streams field, and that's nice. I mean, it's becoming more and more main field topic, which was not at least the case until about 20, 30 years ago, maybe. So that's nice. You would probably see that I started this plot from about 1890s or so, and that's because I went to NASA ADS, and when I tried to search for stellar stream in the abstract, so it was basically back more than 100 years ago that this term appeared, stellar stream. And even back then, they were basically mapping these stars, and they were seeing some linearity of stars alignment in the sky. And they were just wondering what it is and what could be the origin, what are the chances of these stars aligning on the sky. This is, of course, the nebula, the Drift Nebula, which is about 2.7 kiloparsec away, which now with JWST, other things have been mapped with quite clearly. But this study dates back to 1890s. But this concept of stellar stream, or at least the terminology existed, has been existing for more than 100 years. And it was then about 100 years later, then this explosion happened, starting from 90s, when we discovered the disruption of the Sagittarius Dwarf Galaxy, then other streams in Hipparchus, then more streams starting from early 2000 using deep photometric surveys of SDSS, pan-stars, then dark energy survey, and also with Gaia, which basically has shown us the astrometric sky. It has revealed the motion of more than 1 billion stars. So that's one way to look at it, that there's been an explosion in the number of streams in the Milky Way, and how can we use them to do science. But it's along with increasing the number of streams that we have detected, we have also seen that there's complexities that have appeared in all these streams. So as once was thought that maybe stream is just a simple linear distribution of stars on the sky, we see multiple component features, or we see density variations, and so on. So these complexities that we are now seeing in the data has also been increasing. And maybe with LSST, Roman, Euclid, future surveys, we'll probably, along with discovering more streams, we'll probably see that there are more complexities that exist in the stream that we probably do not know as of now. So this is another plot where you have, on the x-axis, you have the year, and the y-axis, you have star mass resolution. The concept of this I have stolen from the cosmological papers that I see, where they try to plot these two things, just arguing for how well their simulation is doing or how much noise-free it is, and so on. So as far as the stellar stream landscape goes, there's not much interesting stuff happening, and to show in this plot. Each of us have our own very tailored set of simulations. But yes, in the early 2000s or so, we were simulating streams where the star mass had a resolution of 100 solar masses or so, which quickly in early 2000 with many different simulation tools came down to about 1 solar masses or so. So can I point on the right? Yes, so it came down to about 1 solar masses or so. So that's we are running quite realistic simulations, because even for real star clusters or real dwarf galaxies, we have stars which are of the same mass as we are running simulations for. But one of the points that I want to make with this is that, again, just reiterating on the fact that as the time went along, we discovered more and more complexities in the stream. So the parameters that we now use to model stellar streams have also been increasing. So initially, we knew that to model a progenitor, you need a mass and you need a scale radius for it. And then you would probably also need a host galaxy, which has bulge, disk, and halo. But along some point, the idea came along that maybe we also need dark matter substructures to explain the heating or the perturbation in the streams. Then around in 2010, there was an idea that the rotation of the progenitor as well, so that's the angular momentum of the progenitor, probably also plays a role. So in the subsequent slides, I'll go over all of this in detail, but this is just a quick overview that what these parameters are and why are they important for different streams. Then there's also the idea that the interaction of streams with giant molecular clouds, with bar, with accounting for dynamical friction in the host galaxy, and probably also MOND, plays a crucial role when modeling streams. Then the incoming of the LMC, the figure of rotation of the halo, the black holes in the progenitor. So there are lots and lots of parameters to explore because each of these actually have an effect on the morphology of the stream, the density variation of the stream, and many other things. So I'll now take a few case studies, stream by stream. So I have three main streams to discuss: Sagittarius, PAL5, and GD1. But just to highlight that how these different parameters play a crucial role, but these parameters are not just specific to these three streams. They're in principle could be applicable to other streams as well. We just need to explore the parameter space. Right. So now I'm specifically in the next few slides, I'll focus on the Sagittarius stream. And so in 95, using I think data from Schmidt telescope or other surveys, pointing surveys in the sky, we found that the Sagittarius dwarf galaxy is actually going under disruption. So you see this elongated feature showing the disruption of the tidal of the Sagittarius dwarf. Soon enough, people started simulating this. At that point, the n-body models were quite simple. You had the mass of the Sagittarius, you assumed a scale radius, maybe a Plummer sphere, for instance, and you threw it in a static potential model, which had a bulge, a disk, and a halo, for instance. And at this point, because all we had seen was the tidal disruption of Sagittarius, no elongated stream was found, people were just trying to model the disruption of the dwarf itself, not necessarily the stream as we now know of. And it was only about 10 years later that in 2003, using two mass photometric surveys, that we actually discovered that this Sagittarius stream actually wraps around the galaxy. So this is a cross-sectional plot of Sagittarius orbital plane. So there were many things that were discovered that is going around the Milky Way, but also that there's an offset of 10 degrees about in the leading and the trailing arm. So that already kinds of this offset already kinds of constrains to some extent the mass of the progenitor. If you have a heavy progenitor, you expect a heavy offset, heavy energy difference in the two arms, but also to some extent the underlying host galaxy, because that decides how the tails are being formed. And so, of course, then there was attempts to model this stream quickly after that. So this is just highlighting that if you have, this is the orbit of the Sagittarius in oblate halo, in spherical halo, and in prolate halo, just to highlight that simple orbits, it takes different forms. So in the prolate halo, when you have more density distribution elongated along the z-axis, you have chances of having higher values for epicenter and so on. And if you have an oblate halo, the orbits are slightly compressed in the z direction. And also you can have the anti-center side of the stream to be appearing closer to the sun, for instance. So the idea is that the choice of galactic potential already affects the structure of the stream, for instance. But this is just an orbit. They also ran n-body simulation of this very rich. So Sagittarius stream is quite rich and complex structure, and what they found is there is no one galactic potential model that reproduces all these features of Sagittarius. So for instance, they found that you have different aspects of Sagittarius provide different constraints on the Milky Way potential. So for instance, this offset in the leading and the trailing arm can be explained only if you have an oblate halo. but the velocities seem to be preferring pro-late halo. So it seems that it's quite complex to model this the system, and eventually I think the authors went along with just showing this plot in a spherical system. So then the story of Sagittarius continues. We had data from SDSS, and this time what we saw is that Sagittarius stream actually has a bifurcation. So it's not the simple stream wrapped around. That's definitely there, but it also has a bifurcation. And this bifurcation is real in the sense that these two components, A and B, are at same distance. They have similar velocities, and they also have similar metallicities, which means that the second component is actually a part of Sagittarius. It's not that it's another stream or it's another wrap, for instance. So then how to explain this bifurcation? So then the idea came along that if the progenitor has a rotation, then the bifurcation could appear because of, during the tidal stripping of the progenitor, a fraction of internal angular momentum can get transferred to the stream during the stripping, and that can create that extra energy, can basically create that offset between the two structures. So here, I mean, they tried different theta. Theta here is the angle between the orbital, the angular momentum of the orbit of the Sagittarius, and then you have the angular momentum of the rotation. So the theta is the angle between the two. And they found that if you have a theta of about minus 20 degrees, so the rotation is in the other sense of the orbital plane as it goes around in the Milky Way, it kind of reproduces this data feature that you see. So this is an n-body simulation. It's not data, but it looks quite similar to the actual data. The other thetas are unable to produce the same feature. So you can actually also constrain the rotation of the progenitor, and it plays a crucial role, especially if you also want to constrain the underlying galactic potential, right? Yes, again, this idea of having this parameter of rotation to the progenitor, it's not something specific to Sagittarius. We found that in Fimbulthal stream, for instance, which is a stream of the omega Cen cluster, you can have this rotation component which can actually make the stream narrower. So actually adding rotation component, because it's adding an additional energy, it's basically making your stream narrow or wide, for instance. And we know that this internal rotation it's common phenomena in the globular clusters and the dwarf galaxies that we observe for the Milky Way. So something to account for instance. Then the story of Sagittarius continues in Pan-STAR survey in 2017. We find that additionally, there are these clumps and bumps and spur features in the Sagittarius that you're now seeing here that goes out to 100 kiloparsec and beyond. So these are just clumps in the phase space that are likely associated with the Sagittarius stream. So then how to account for these features? And so there were additional parameters that were included in the n-body simulation. This time, our colleagues had, to model the progenitor, they had the stellar halo of the Sagittarius dwarf galaxy, but they put it inside the dark matter subhalo of the Sagittarius. So this is the dark matter subhalo particles of the Sagittarius stream, and these are the star particles. That's one parameter. The second parameter was the dynamical friction was introduced. And what dynamical friction does is that it allows Sagittarius to have an infall from larger distances. So now you can be, because the epicenter and the pericenter now shrink because Sagittarius is a massive system. The dynamical friction plays a crucial role on its modeling. So you can allow its infall from much larger distances this time, and which can eventually produce these arms which probe distances out to 100 kiloparsec and beyond. So qualitatively explaining the data, these bumps and spur and features we see. So then accounting for dynamical friction, to some extent also becomes important when modeling Sagittarius or any other stream from massive progenitor, for instance. And then yes, with Gaia DR2, it gave us really nice velocities for Sagittarius. So we saw that while you have a stream track pointing in one direction, broadly speaking, you have the proper motions misaligned and pointing in other direction, a telltale sign of perturbation. So Eugene and team, they ran these n-body simulations. So this is without LMC and this is with LMC, and it's with LMC that you're able to, and assuming certain potential model for the Milky Way, they are able to reproduce qualitatively this feature that we are seeing, the offset in the proper motion direction and the stream track. So then it's important to consider the LMC and its properties as additional parameter when you're modeling streams of the Milky Way. And yesterday from Neil, we heard about the figure of rotation of the halos that we generally see in cosmological simulations. So far had been thought they're probably not so significant to affect the dynamics of the stars or stream in our galaxy. But actually, if you assume a figure of rotation, then the Coriolis acceleration forces that come into play can actually alter the Sagittarius structure by 1 degree, which is in principle measurable, right? So, I mean, all of these parameters actually become a bit crucial for modeling Sagittarius or maybe other streams as well. So the point that I'm trying to get at is that at least for Sagittarius, if you want to model it, different people have explored different parameter spaces, so subset of this parameter, but maybe in reality, we want to model the stellar halo of the progenitor with the rotational component, the dark matter with the rotational component, and then you have the host galaxy with bulge, disk, dynamical friction, LMC, and probably the rotational component as well. It's difficult to do because your parameter space really explodes, let alone trying to fit for these parameters when you're analyzing the data. So that was one example of Sagittarius. And there are too many parameters to consider, I understand. But then this is Palomar 5, which is a stream from a globular cluster, different class of stream, low mass progenitor, looks quite simplistic, discovered originally in 2003 in SDSS. And instantly, people started running n-body simulations of this, finding that trying to produce these streams and how could this be formed, finding that the formation of tails is dominated by the disk crossing at the pericenter of PAL5 globular cluster. But until now, no really density perturbations or overdensity features were seen in these simplistic n-body simulations. Then the story continued. We had SDSS DR8, and we saw that Sagittarius is actually not 10 degree, but even longer stream, 23 degrees, and you have the trailing arm and the leading arm. But this time you can see some over and under densities along the stream track. So why do they exist? And these are, in fact, authors argue that these are in fact significant. So they've found these 5 gaps, which are quite significant. And one of the ways to explain these is via perturbations of thousands of dark matter subhalos within 30 kiloparsec of radius. So that's one way. The other way is probably if you consider the interaction of Palomar 5 stream with the giant molecular clouds which are in the disk. So you have the disk with the giant molecular clouds rotating in prograde direction. Palomar 5 too has a prograde motion. So because the relative velocity between the giant molecular cloud and the PAL5 is less, the interaction increases and the perturbation effects also increases. So then the authors see these some gap features that you're seeing here, which is purely coming due to interaction with the giant molecular clouds, for instance. Then people also try to detect PAL5 in Pan-STARRS 1, and they saw this clear asymmetry between the trailing arm and the leading arm. So SDSS coverage, I think, was only down to here. So we couldn't see leading arm in the SDSS, but now we had a wider coverage around PAL5 with Pan-STARRS 1 dataset. But we saw that there's this clear asymmetry. So if we are in Newtonian dynamics, we expect the 2 arms to be of similar length. What could be the cause for this asymmetry? So then we introduced additional parameter to model the PAL5. And this was that because of the rotation of the bar, as the bar sweeps by, some stars experience difference in net torques near pericenter. So it doesn't necessarily truncates the stream, but yes, it definitely causes this underdensity, which it may become difficult to detect in the photometric surveys, at least. The other way to account for it is maybe work in the MOND paradigm, which is different than the dark matter paradigm. But the idea is that this asymmetry that we see in stream is a natural consequence of MOND, because MOND causes lopsidedness in the progenitor, and because of this lopsidedness, you have one part of the progenitor releasing more stars during tidal stripping, and the other side releasing less stars, which naturally creates this asymmetry. So this is the lopsided distribution of PAL5 that you can see here, and this is They're comparing their simulations in blue with their data in green, for instance. But yes, I mean, more simpler scenarios is, of course, if your stream is on near resonant orbits, then you can have these fans and bifurcation features, which are less dense than the narrow, dense stream that we see, which could again make it difficult to find in your detection algorithm or technique or whatever you're using. Yes, and then the other things to consider is if you are interested in constraining the mass of the progenitor to run your n-body simulation, you need to have the knowledge of the mass. The detectability of the stream itself places some constraints on the mass of the progenitor. So there was this really sleek, nice work from Eduardo and team, and they show that the fact that we are able to detect stream, the PAL5 stream basically suggests that its mass to be about 4,500 solar masses. And if you consider a 3 times more, so this is n-body simulation, not data. And if you consider a 3 times more massive progenitor, then you would really not see the stream. If you come to think of it, this is counterintuitive because if you have a massive progenitor, you expect more tidal stripping to be happening. So you should be able to see stream, but this is an STSS mock data set. But the fact is that if you have a massive progenitor, that means you have more number of stars. That means you have more number of low mass stars as well, which means you have more number of low luminosity stars. And so it's more number of low luminosity stars leaving your progenitor, which basically becomes really difficult to see given the shallow depth of SDSS, for instance. So, I mean, this was an interesting study. The other parameter to maybe take into account is the black hole population inside your progenitor. So, for instance, PAL5, if it has no black hole population, nearly 0% of black hole population, then you'll probably not see the formation of stream. It's difficult, but if you keep on increasing the black hole population, then you find the formation of the stream, likely because the black hole, not likely, I mean, that's the physics, that the black hole inflates the cluster, enhancing the tidal stripping as it happens. So that's your another parameter to account for. And then, yes, we have heard about the tilting of the disk that can potentially make the stream narrow. So here they are comparing the data in red with the tilting disk in blue, and the green one is in static disk, so the green stars are wider than the black stars. But again, I mean, one of the points I would also like to highlight is your n-body simulations. We try to reproduce the stream data, but the stream data itself depends on the selection function that you use. So how do you know that a given star, in fact, belongs to your stream or not? And that's quite difficult to do. So for instance, here I'm comparing the identification of PAL5 stream in 2 different data sets, and authors followed different techniques to find it. One in DECCALS, which is a photometric survey, no kinematic information. Then you have Gaia data, where you have the additional kinematic information. And in photometric survey, you see this asymmetry, but in Gaia, you see that the PAL5 is probably symmetric. So the selection function actually plays an important role, and then you want to, of course, simulate the stream to learn the science, what's happening. Yes, again, so just to reiterate what I said really fast, maybe, that for progenitor, for running n-body simulation of PAL5, people have played around with different parameters. So for progenitor, it's important to consider the mass, the scale radius, and now also the black hole population, as we know. And for the host galaxy, we know PAL5 would get affected by the properties of the bar, the tilting of the disk, the halo, of course, you need in your modeling, the GMCs. And then after this, additionally, you can consider if you want to go in the direction of MOND, or you want to put in a population of dark matter substructures, and so on. Right, so this is the last stream that I'll discuss now, GD1. And I'll again, we'll see how the story of GD1 evolved. So detected in 2006 in STSS as a 63-degree long stream. It's a photometric survey, STSS. And again, we started to analyze, we saw some underdensities and so on. We started to analyze the gaps, the underdensities, dark matter substructures, possible interaction with GMCs. With GMC doesn't necessarily interact because GD1 is going in retrograde direction. GMCs are in prograde, so the interaction time is less. Then again, we have seen this plot that you have the GD1 along with the spur, as we observe in Gaia-DR2 and Pan-STAR survey. And one of the ways to explain is that if you have a very dense perturber creating the spur. And here is another view of GD1, the same structure, using different detection techniques. So this is machine learning-based stream detection using a software called Via Machine by David Shea and collaborators. And here they are comparing their GD1 data with the data of Adrian and Anna. And they find these subtle differences that you can see, although not so much, but some subtle differences in the density features along the stream. And so it really then the idea is to simulate what science we can learn with these different data sets of the same stream that we have in hand, which can maybe change your final science results. We now know that GD1 could potentially also have perturbed by Sagittarius. So here you have GD1's phase space coordinates, so the position space, the distance of GD1, proper motions, radial velocities as a function of the length along the stream. When you have no Sagittarius, so in this case, GD1 looks much simpler compared to when you have the massive Sagittarius acting as a perturber, and then you see this another stream kind of which seems to be different than GD1, but it's really not. It's just a component of these stars got perturbed to different orbit. So for instance, if we find this additional stream that we are seeing here in our data set, in Gaia or otherwise, that could confirm its perturbation from Sagittarius. I'm not sure if we have found the stream yet, but that would confirm. But this is again just one of the Sagittarius model. You can try different Sagittarius model of different masses in different Milky Way potential. And again, GD1 is not the only stream that's been shown to perturb by Sagittarius. You have Jhelum, the multiple. We now know that Jhelum is quite complex. It has these multiple components that you're seeing. And one of the ways to explain this is potential perturbation by Sagittarius, right? So the story of these once thought simplistic streams is actually quite complicated. Yes, so now I'll spend a few time just talking about GD1 and Cocoon. Some of the work that I have done is it's a different view of GD1 using Gaia data. So we see that GD1, this study is from 2019, that GD1 we see there's this narrow and dense component surrounded by this broad diffuse component that you see. So why is this? Why does this happen? We constrain the width of the narrow component to be about 30 parsec, the width of the wider component of about 110 parsec. So it's statistically significant, the Cocoon component. Recently, in an independent study by the DESI collaboration, they found they find much wider Cocoon around GD1. So they basically do the calculation and they find the narrow components is 50 parsec, dynamically colder compared to the broader component, which is about 450 parsec wide and 5 kilometer per second velocity dispersion. So then what could possibly explain this Cocoon component around GD1? There's additional interesting thing about GD1 is that there's a stream, shear, that crisscrosses GD1 on the sky, but it actually lies along very similar orbits. So this is the orbits of shear and GD1 along with the data points in the proper motion space, in the radial velocity space. The metallicity distribution functions are different, which means they are different streams, or maybe they at some level it also argues for a group infall, maybe that these two were globular cluster inside a parent dwarf galaxy, or maybe shear is the stellar halo of the parent dwarf galaxy, GD1 was the globular cluster going around. But we got interested in this idea that maybe GD1 represents one of those streams where it evolved in the parent dwarf galaxy and then accreted into the Milky Way because of these different features that we were seeing. Along the same time, Ray Karlberg had this paper showing that if you have a globular cluster pre-processed inside a subhalo, and then which eventually later accretes into the Milky Way. So what happens is that some of the stars are already stripped inside the subhalo, and when they accrete, they end up forming this broad Cocoon component that you can probably see here, maybe on the television screens. But once the globular cluster gets deposited into the Milky Way, it continues to strip, forming the narrow and dense stream that you're seeing here. So these are different examples from Karlberg's simulation. But of course, because everything's happening along a similar orbit, the broad component and the narrow component lie along very similar orbits. So we were headed towards this direction in exploring this idea of accretion of GD1. And this is Karlberg's fully fledged simulation of formation of globular cluster streams in the lambda CDM paradigm. On the left-hand side, you're seeing all the particles you're seeing are globular cluster particles, and they're producing streams. So you have more number of streams in the inner regions of the host galaxy, and then they are being pre-evolved in their subhalos and then falling into the host galaxy, giving quite a realistic picture of how these streams would have formed. And we know that if not all, at least most of the globular clusters and streams in the halo of the galaxy would have in fact been accreted inside their parent galaxies. Then this brings in an additional parameter that maybe we should also consider: the parent galaxy of the globular cluster that we are trying to model, for instance. So then we instantly got interested also in the idea that could these accreted globular cluster streams, can their present day properties, their width or their velocity dispersion, tell us something about the dark matter distribution of the parent galaxy, which is probably now being destroyed, but we still want to see if we can recover some dark matter properties of the parent subhalo. So then our n-body simulation, the idea is pretty simple, is that we consider code subhalo models and we consider few of the cuspy subhalo models, motivated both by the CDM, the NFW, and also by self-interacting dark matter or other dark matter models. Inside these subhalos, which have different properties, we inject the globular cluster, and then we let it fall, accrete into the host galaxy that you're seeing here, and then we can compare it how the resulting n-body streams compare to the data that we see, for instance. So this is, in principle, we run nearly 100 n-body simulations, but this is just one example. So we have the n-body parent subhalo shown in blue here. We have the n-body globular cluster shown in red here. And initially, and these are times that I've mentioned, and initially the globular cluster evolves within the parent subhalo as it accretes orbits around the galaxy. And so you can see that the tidal stripping of globular cluster already starts within the subhalo. At some point, globular cluster jumps into the Milky Way halo, while some of the stars remain bound to the parent subhalo. Some of the stars also get ejected from the subhalo, but the evolution continues and so on. So all of this ends up giving quite complex looking streams that you're seeing. So all of these are globular cluster particles. These correspond to few examples from the code subhalo case. And on the right-hand side, you have globular cluster stream examples from the cuspy subhalo case. So you can see this simple introduction of the idea that you had a parent dwarf galaxy introduces lots of complexity. So we see in these streams that you have the narrow component, you have the cocoon component, in some cases also these secondary components, spore-like features, and the density variation. Mind you, in our host galaxy, we had no dark matter subhalos. It was a static, smooth potential, but still we get these density variations. And so then this is the prediction that we had, for instance. So here on the x-axis, you have the physical width of these different streams that we model, and on the this x-axis you have the velocity dispersion. So we are trying to make prediction based on the observables of stream, their physical width and velocity dispersion, and the y-axis is basically just different simulations. So each point corresponds to a given stream. So these are what we call the in situ streams. So these streams are basically where there was no parent subhalo. So they end up forming streams of about 50 parsec wide. These are just simple globular cluster, and about 1 to 2 kilometer per second in the velocity dispersion, as we expect from simple globular cluster streams. Then these small circles and big circles basically represent streams in a higher mass and in a lower mass and a higher mass code subhalo. And I plot them as two Gaussian distributions that you're seeing here. So we expect these streams to be about 200, 300 parsec wide, taking account their cocoon component, and to have a velocity dispersion quite spread of about 3 to 4, 5 kilometer per second or so. And then these small diamonds and black diamonds here on the second plot are basically streams in a lower mass cuspy and a higher mass cuspy subhalo, and the streams end up being quite wide physically and also dynamically quite hot. And the reason, and if you're wondering that what could be the reason, it's simple, that if you have a globular cluster evolving in a code subhalo and a globular cluster evolving in a cuspy subhalo, because in code case, the forces are rather compressive. So the globular cluster, ideally, in theory, undergoes no tidal stripping, but in n-body simulation, it does, but the stripping is really less. Compared to a cuspy case, where the density really is quite cuspy, so the tidal stripping is very large. And the strip stars basically end up occupying the phase space volume within the subhalo. So once this subhalo, it falls into the galaxy. So this is an isolated case, isolated subhalo with a globular cluster. But once it falls into the galaxy, the cuspy case basically ends up producing, the globular cluster from the cuspy subhalo ends up producing really wide stream and dynamically hot compared to the chord case. So this is the same plot again, but here I'm simply comparing the measurement of GD1 that the DESI people found. So this is where GD1's current measurement lies in terms of width and also in terms of velocity dispersion, seem to be favoring these limited, the code model. But again, we tried very limited set of simulations, right? In principle, we should have tried 1,000 or 100,000 simulations. It's computationally challenging. But the main takeaway is that globular cluster streams from chord subhalos indeed form wide and dynamically hot streams, but in cuspy cases, it forms even wider and dynamically hot. So with this, I'll hope I'm in time. The summary or the main takeaway of this was that there are lots in principle for realistic modeling of streams. There are lots of parameters now that we know of to consider. So for instance, if you're modeling a dwarf galaxy stream and you want to consider you're modeling its progenitor, you have the star component to take into account, also the rotational component of it, and then also the dark matter component. Since you're considering dwarf galaxy, in case of globular cluster, you might also be interested in probing the parameter space in terms of the black hole population, for instance. Same for the host galaxy. We know that there's a bar at the center. You have the halo. The disk might be tilting, which additionally contains giant molecular clouds affecting the stream, the Sagittarius, LMC, the figure of rotation of the halo, the dynamical friction. So it's scary, but it's also interesting. Then you, of course, have the parent galaxy that you might want to consider if you see a cocoon component around the stream. And then again, the same parameters, right? The possible rotation that the initial parent galaxy had, its size, and so on. In principle, there are other baryonic effects to, if you think of it. They could be, if you find a stream that's perturbed, it could be due to also because of some dwarf galaxy or globular cluster that has not been discovered yet. So maybe some of the GD1 perturbers that we have found could actually be a dwarf galaxy or a globular cluster that LSST, we might find in LSST and so on. It could also, the perturbation could also be in the streams, the perturbation could also be due to some of the other progenitors of streams which are now disrupted. I mean, there are lots of possibilities that exist, but yes. So thank you for your attention.
Yeah, that was a great talk. Thank you so much.
Thank you.
Hey, great talk. I was wondering if when you have this broader this cocoon feature, you always have to find a narrow one or another like a narrow component, or you can find only the broader one.
If you find so I mean the idea of this cocoon component was that if you have a globular cluster stream, and one of the ways to one of the telltale signs of globular cluster stream is that it's quite narrow. And so if you see a narrow and dense feature, and around that you see some more distribution of stars that lie along similar orbits, have similar metallicities, for instance, basically saying that it's coming from the two stellar populations are same, lying along same orbit, then that's possibly due to the progenitor globular cluster being evolved inside the parent dwarf galaxy. If you see just a broad component, then a likely first scenario is to consider is that it's probably a dwarf galaxy stream. Right?
Thanks.
In the simulations you showed at the very end.
Sorry?
In the simulations that you showed at the very end. So I guess in some of Ray's simulations, you have kind of something that still looks very much like a stream in the subhalo, then that gets disrupted in the Milky Way. In the very last video you showed, that looks like a much more phase mixed thing, which then disrupts in the Milky Way. So maybe first question, does your suite include, you said 100 simulations or so, do you have kind of both types, or are they all evolved for a long time and mix into the subhalo and then disrupt?
So this
in the
case
Milky Way?
that I was showing, so the green particles are the subhalo particles,
Mhm.
the red particles are the globular cluster particles, which are just isolated case. So I mean, they're not being thrown in the host galaxy right now. It's just
But then you throw it in later.
no. So everything happens within the time period of 8 gigayears. So within the 8 gigayears, we initialize the subhalo inside the host galaxy, and inside that we have the globular cluster, and then this just evolves in the host galaxy. So from the beginning of the simulation, the system is inside the host galaxy.
So I guess where I'm going with this is,
Yeah.
presumably there's also a dwarf galaxy in this subhalo.
Yes. You
And
mean
so-
the stellar halo component?
Well, so I'm trying to get a sense of the scale of the stars that belong to the dwarf and not the globular cluster here. And
Right.
whether, in the video you showed, maybe, I don't know if you want to play it again, but eventually the stripped stars from the globular cluster look like almost spherical in this subhalo.
Right.
Which, if they have a very different chemistry and scale radius than the stars in the dwarf, maybe you can tell them apart. What I'm wondering is, do you expect to find the cocoon overlapping with basically a dwarf galaxy stream, or can you find it separate?
Right. I mean, so in principle, if the chemistry is similar, then of course it's difficult to, in principle, you could have the stellar halo of the dwarf galaxy will have the same morphological feature for sure. But if you could tell them apart with chemistry or maybe with metallicity, so then it will be.
But you think you always expect to find it overlapping with the dwarf stream?
The stellar halo of the dwarf and the globular cluster stream, yes, the expectation of them. But again, we haven't taken into account the dynamical friction. For instance, so it could be that, I mean, let's say you have a dwarf galaxy and you have a globular cluster orbiting at the outskirts of the halo. So maybe at some point the globular cluster jumps into the halo. If the parent subhalo is still massive, so eventually because of the radialization or maybe the dynamical friction, the subhalo might sink to lower energy orbits compared to the globular cluster. So this was a very simplistic simulation that we ran. Lots of other parameters that I basically showed in my last slide are not taken into account. So it's not a perfect simulation, but it gives out that idea, the formation of cocoons.
Hi, very cool talk. I guess a related question is, I mean, given the types of dwarfs that host globular clusters, they tend to have a lot of stellar mass. So has anyone simulated, a kind of dwarf with the right stellar mass with one of these globular clusters inside, and then seen like how detectable the dwarf galaxy stream is compared to the globular cluster stream? Like, could it be, because I mean, for the like GD1, we don't see any obvious dwarf on exactly the same orbit or nearby. But I'm wondering, like, how observable would those dwarf stars have been given the expected, stellar mass?
So in a few of our, I think in 2 or maybe 5 of our N-body simulations that we ran, we did have the dark matter subhalo, we had the stellar halo, and then we had the globular cluster. So of course, I mean, they overlapped, but then again, it was a very simplistic simulation. But then, I mean, so this is the data, right? So you have the GD1 stream of one stellar population, then you have shear of the other population. And then, so could shear be the stellar halo of the parent dwarf galaxy, because it's also slightly metal rich, if you see, or could it be just another globular cluster? So for instance, yes, I mean, so then how to, probably by having more chemistry, if we see some sodium, oxygen, anticorrelation and stuff like that, we might be able to say more about, we know GD1 is a globular cluster stream, we might be able to say something about shear, if it's a globular cluster, if it was the stellar halo. But we do see, I mean, we know of other streams as well, right, which have similar actions or similar angular momentum energy as that of GD1. They're not as similar as sheer, for instance, but they are kind of clustered together. If not sure if that answers, but
Thanks.
okay. So
Hi, Kati. Thank you. That was very insightful talk. So I don't know much about like globular cluster formation or origins, but what do we have an expectation for how many we think would have been in situ versus in dwarf galaxies? Or in other words, should we be expecting cocoons around every globular cluster stream that we find?
do we have Chiska here? Do you see something in your simulations? Do we?
Well, I'm not sure. I can answer. I think is Carl here? We have a globular cluster expert.
Right, but
No, Carl.
yes, do you want to say something or?
Uh,
I mean,
I-
you're running some simulations right now, right? So that's why I'm putting you
Yeah.
on the spot. I can answer maybe from the perspective, my own experience and also looking at Ray's simulation, but you're doing something new and interesting.
Okay, yeah. So to explain a bit, so I have a summer student working on simulations with many globular cluster streams, not globular clusters, inside a subhalo that's falling in, where the host halo is also alive, which is, I think, the main difference.
Right.
And what we see is that so we're just starting to analyze it. But what you see is that the distribution of orbits and actually also energy and angular momentum of the streams after the infall, after the subhalo stripped and the streams are stripped out of the subhalo, is actually pretty large. So I wouldn't, based on that, I wouldn't necessarily expect to find things on very similar orbits. There's some similar range in orbits, but there is some diversity there,
Right.
which yeah may complicate this.
That's
But
probably
but the question was more like, would you expect all the globular cluster streams to be from accreted dwarf galaxies, and thus have a cocoon around them? And yeah, I don't think I can answer that with these simulations.
I mean, you'd find them to be complex, of course. Maybe you will not have a very, I mean, so Ray had more than hundreds of these globular cluster streams, right? I just picked a new nice ones, which showed this narrow dense feature kind of in the middle of the cocoon. So for an easier comparison with the data. But in principle, I mean, Ray simulation had lots of different, sometimes the cocoon had an offset from the mainstream, sometimes mainstream was ahead of the cocoon. So it's a very dynamically complex process. So you might not see the narrow stream and the cocoon in this simplistic fashion every time. But yes, you might find some broader component which has the Stapler population more or less maybe along the same orbit, and then you can try and explore ideas.
So at least from a model perspective of globular clusters, there's large disagreement on where exactly globular clusters form, especially going down to the dwarf regime. Some models say they, in general, form in more massive structures at 10 to the 10 solar masses and above. And there's other models that can seed them in smaller dwarf galaxy-like structures. Then again, the understanding of how does star formation actually occur in these very low mass systems at these really high redshifts is really, really uncertain. And then the second problem is the disruption of globular clusters is exactly as poorly understood. And so I think it's, at least from the theoretical side of modeling globular clusters, super unclear how many would be falling in with dwarf galaxies versus more massive structures. How many of these dwarf galaxies would be expected to have any globular clusters at all? And then in terms of tidal stripping, how many of them would have to be stripped at the same time?
So I know, for instance, Eridanus 2 dwarf galaxy. It has one globular cluster, and it has assumed to have a halo mass. I think it's coming from measurement, of course, of about 10 to the 9. M200 is about 10 to the 9 solar masses. I think that's one of the least least massive dwarf galaxy that we know of hosting a globular cluster. For instance.
We have a question online. Maybe first, I heard you say that stream perturbations could be because of as of yet undiscovered globular clusters in dwarf galaxies. Were you referring to the gaps seen in streams?
Yes, I was referring to the gap that if you have density perturbations, I mean, you could have lots of old progenitors that are probably now disrupted to form stream that might have perturbed the stream in the past. You could have lots of, I mean, we are now discovering lots of faint systems with deep photometric surveys. We'll continue to do so with LSST and so on. So yes, there are lots of undiscovered objects with stars that might also perturb the stream. So yes, in principle.
I was on. Thanks a lot for this really nice talk. It was super insightful. I was wondering, maybe you did mention it briefly and I missed it. Does the cocoon actually have a different metallicity to the stream itself?
So I mean, if it's coming from the same globular cluster, then the metallicity distribution of cocoon, I mean, as far as the simulation is, I mean, it should have the similar metallicity as that of the main stream. We personally, as far as the data of GD1 is concerned, we don't particularly see any offset in metallicity between the cocoon component and the narrow stream. I haven't looked very, very carefully in the DESI. People, I think they do make a metallicity cut to find the GD1 stars, but if they actually do a statistical analysis to account for if it's different metallicity components, I'm not sure if they have done that. But yes, I mean, if we find a difference, then that would be make for a different science case. Maybe so this cocoon could probably be coming from the stellar halo in which the GD1 came. But as far as my knowledge is, there's no metallicity offset between the two.
Thank you.
Yeah, and just to touch briefly on the number of globular clusters per subhalo, right? I think it increases with subhalo mass, but at some point it flattens out. So like these ultra faints, they tend to have one globular cluster in them more often than they should have if you just extrapolate the scaling relation. But also just a point to make is that very often, if not always, the ultra faints have globular clusters that are very close to their centers. Would you expect these pre-processing of yours to work in that case? Or perhaps they are close to the center because of dynamical friction, something like this? Did you incorporate these things in your simulation?
Right. I mean, if you have massive enough cluster, then it will probably sink to the center, for instance. I think that's the idea. We only tried, I mean, it was 100 simulations that we ran, and there was already, in principle, lots of parameters to probe, but we tried we tried lots of orbits of globular cluster within the subhalo. We haven't tried too close. So I think the minimum distance that we had from the center of the subhalo of the globular cluster was 0.5 kiloparsec or something. But yes, I mean, your point is if it's 0.1 kiloparsec or even less. So you're referring to, I think, the Eridanus system. Yeah. Right. So, I mean, again, this simulation was actually not to reproduce GD1 data or any specific stream. It was just a very generic. We basically were trying to, the idea was that Ray Karlberg, he has this simulation, just have a higher resolution simulation and then see what features can we get. Maybe we can get more detailed features with these very tailored simulation. So yes, and I think coming back to the globular cluster formation in low mass dwarf galaxies, I think at low mass, the process of globular cluster formation becomes really stochastic. So we see that it's one with large uncertainties also and so on. Yeah.
So coming back to this asymmetry in PAL5's tidal tails, and the difference between I think it decals and Gaia.
Right.
So I tried looking for the feature that in Anna's 2020 paper in the Delve data, which is at these latitudes simply every reprocessing of the decals data, and I couldn't find the fan. We never wrote that up because this was just meant to be like in a little example of the public data release paper, and no one wanted to write a more like a more detailed analysis of that, but I'm wondering if how you think of if we're putting too much effort into modeling features and not enough effort into modeling things like selection functions or what we don't understand about the data.
So I mean, your question is that if you are putting similar conviction in selection function or not compared to the modeling of the streams.
Sure. Yeah.
No. I mean, it's a complex exercise, right? I mean, it's again coming back to the same idea. I think Adrian had a study. Maybe other people have also had a study. I think Adrian's study was also on Palomar 5 that he provides membership for each star. So I think people are doing that kind of studies where they provide membership of the star, or they do it more statistically by sampling. You have a given set of stars, sampling to see how statistically the stream looks like and so on. It would be nice to have a stronger selection function, a convincing selection function for sure. But yes.
Sorry, just a question from a noob. So when you try to model some feature that you observe, do you put it through a forward model of the instrument with some crude, at least, selection function? Or do you just take those as the given stars and then try to n-body simulate that with no selection function? Just curious how you actually do it.
Could you repeat? No, sorry. So how we run n-body simulation?
No. So yeah, when you actually try to fit a feature, do you try to model the selection function and put it through the instrument?
I mean, generally at large, as my knowledge is, no, not really. So we have the present day information of the stars. We have the present day, if you're lucky, 6D information. If not, you at least have the 5D information, or for the very least, you have the position and the distance gradient from your photometric survey. So you have that in present day. You try the different initial conditions for your progenitor, different mass, different scale size, different original position related to the present day. And then you try to fit it, and that's it. So you look at the present day data. I don't think yes, until now, I don't think at large we have cared about the selection.
So you don't pass it through the instrument, like a model of the instrument?
I mean, so again, hold on. So, I mean, people do that. So we are comparing with the observables. Right. So when we compare in the observable space. So I think that's probably in effect, we are doing a fair comparison for sure. But it's also not so simple, right? So for instance, one of the things that we could compare for is if the n-body particles have similar luminosity as that of the stars that you see in the photometric surveys. I'm not sure how many. We have just n-body particles so yeah, but the stellar population accounting for the intrinsic stellar evolution of progenitors, it's also important. I mean, black holes and stuff like that. So, yeah.
Awesome. If there's no more questions, let's thank Yati again.
Thank you.
Again, one more thing. Do you have any questions for discussions, like one or two that people could talk about?
Oh, yes. Don't need to. I mean, it's just also to do with Alex's question regarding the selection function. I understand that it's a theory workshop, and I respect that, although I still had a few data-related thoughts to show. But that's definitely there, the selection function. I know the talk was, I mean, my answers were quite at the surface. Maybe they were not very direct or very convincing in one. But the idea is, I mean, in reality, there's just lots of parameters to take care of that we now know that makes it really challenging to, and then it basically boils down to what science case you're interested in probing, right? So maybe you don't care about the black holes, or maybe you do not care so much about, you have an idea that maybe fine galactic potential, whatever range it is, it will probably not perturb the stream in this way. So I will not go down that road. I'll probably just do this. So yes, I mean, you could look at it at stream by stream basis, which parameters you think are really important for this particular stream. But that you can also, the knowledge you can gain is only by experimenting with these parameters, right? So which parameters actually become a dominant factor for a given stream and so on. So yes, I mean, I don't particularly have a question. I think everything's on the table right now. The data, the quality of it, the selection function, and also the n-body